part 3 of the revision video. Let's go. Okay, I'm finding where we got to last time. It was here. Right, so extraction of aluminium from its ore, aluminium oxide, or from its ore, which is bauxite, which contains aluminium oxide. And the reason we can't extract it using carbon displacement is because aluminium is more reactive than carbon, so can't be displaced by carbon, unlike iron. Now the first problem with this process is the melting point of aluminium oxide, and the reason it's so high is because aluminium forms 3+ ions and oxide is 2-. Now you can imagine that in this giant ionic lattice there are incredibly strong attractions between the oppositely charged ions, because you've got 3+ and 2- ions. So those are quite big charges to deal with. So explain why obtaining molten aluminium oxide is difficult, because it's got a high melting point, so a huge, I think I underline it because such a huge amount of energy is needed. And so cryolite is used. Now cryolite needs to be heated to a pretty high temperature, probably around about 1500 degrees Celsius. But at these temperatures cryolite becomes a liquid, and when you put aluminium oxide into it, it dissolves. So aluminium oxide dissolves in the molten cryolite, and it dissolves in the molten cryolite at a lower temperature than the aluminium oxide melts. And of course we need the aluminium oxide to be liquid because we need the ions, the Al3+ and the O2- ions, to move. And in this reaction our O2- ions will be attracted to the positive electrode, and at that positive electrode, the anode, you'll form oxygen, and of course you'll need 2 oxide ions to form oxygen, and the charge on the left hand side of the equation is 4-, so 4 electrons are kicked out, and because we're losing electrons, that's referred to as an oxidation. And the aluminium ions will be attracted to the negative electrode, and when they get there you'll have aluminium 3+, okay, and each one of those will gain 3 electrons to form aluminium, okay, and that is a reduction because the aluminium ions are gaining 3 electrons. So here you're being asked to identify what's been oxidized. Well, we've already answered that. It was the O2- ions, because they lost electrons. And if you were going to use the name of that species, that would be an oxide ion. Now, unfortunately, in this process, you've got oxygen bubbling up around the positive electrodes, and this process is being done at extremely high temperatures, and these electrodes are made of carbon. So the oxygen reacts with the carbon anodes to form carbon dioxide. So we're turning the solid carbon into gaseous carbon dioxide. So the anodes are corroded over time, so need replacing. Now this is a question about the structure of aluminium. But before we go on today, you might be asked questions on aluminium extraction, and they might say, well, why is it such an expensive process? And the answer to that is not that the electrodes need replacing. It is in fact because a large amount of electricity is needed in this process, and it needs to be done at a very high temperature to ensure that the cryolite is molten, and hence the aluminium ore is also molten. So those are the two reasons why it's an expensive process. A lot of electricity is needed and high temperatures are needed. Carbon, which is used in the anodes, is pretty cheap. So the next part of the question asks you about the structure of aluminium metal. So it's really a question about metallic bonding. Now, metallic bonding is the attraction, between the positive metal ions and the sea of delocalized electrons. So the structure of aluminium metal, you'd have a regular lattice of, and rather than just saying positive ions, let's make it specific to aluminium, a regular lattice of Al3+ ions. Okay, and these are attracted to a sea of delocalized electrons. And these delocalized electrons can move. I'm going to use shorthand here. Delocalized E- can move, and therefore aluminium is a very good conductor of electricity. Now, I've just included a quick question about the production of ammonia with some real sort of fringe bits on the syllabus here. Now, the raw material from which hydrogen is obtained, it's actually really obtained from the reaction of two substances. You need natural gas and water. And natural gas contains methane. And the methane reacts with the water to produce hydrogen and carbon monoxide. And obviously, if you're going to write a chemical equation, it needs to be balanced. So let's have a look at balancing it. We've sorted the carbons. We've got one there, one there. We've got one oxygen there, so that sounds okay. We've got 6 hydrogens on the left, so we have 3H2 there. And another knowledge recall question: name the catalyst used in the production of ammonia. It said name it, so we can't use a symbol. It's got to be iron. And on to the next question. This is an organic question on ethanol, and initially we're asked to compare different processes for producing ethanol. So, Company A is located in an agricultural area, and they require ethanol to produce vinegar, and they only need a dilute solution. Now, you've got two processes. We could use fermentation, or we could use the reaction of ethene with steam. Now, Company A, because it's in an agricultural area, is probably better off using fermentation. Okay, and that's principally because the agricultural area, the agri area, can grow the sugar, which is the raw material used in fermentation. Now, Company B isn't near an agricultural area. It's in a semi-desert area, so it's probably not a very good place for growing sugar. And they're going to use the ethanol as a solvent, so we'd want very pure ethanol. Fermentation only produces a solution which is 15% ethanol. But as Company B is near an oil refinery, that would be a very good place to obtain the ethene required in the other process, the second process, the hydration of ethene. So method used by Company B, the reaction of ethene with steam. And you need to highlight that it's near an oil refinery. So easy supply of ethene. You could also say that the land in a semi-desert area would be very poor for growing sugar. And here you can see we've got ethanol at the centre of this table, and there are 3 reactions which you could do with ethanol. Now the only one which is still on the syllabus is this one, converting ethanol into ethene, and that's a dehydration reaction, and you take the ethanol and you heat it over a catalyst of aluminium oxide, so Al2O3, and that forms ethene, C2H4, my goodness, my writing is getting even worse, and water is removed. And as I said, that's a dehydration reaction. Right, I'm going to try and rattle through this question before the end of my 15 minutes is up. This is a question about the blast furnace, and you're expected to fill in the gaps really in the on the diagram. So you can see here at the top, into the process we put coke, limestone and iron ore or hematite, and down at the bottom here you produce molten iron, which can come out the bottom of the blast furnace down here, and floating nicely on top of the molten iron you get a substance chemists refer to as slag. Now in the furnace we have carbon which is contained in the coke, okay, and that reacts with oxygen to form carbon dioxide, and this is an extremely exothermic reaction, and it provides heat to the furnace. And the reason so much heat is required is because actually a very good reducing agent is carbon monoxide, and this will form when you react carbon dioxide and carbon together in an extremely hot environment, and it's the carbon monoxide which then reacts with the iron oxide which was in our iron ore, and this reaction will only occur in very hot conditions because this reaction is endothermic. And that concludes the 3rd video.